Hello, everyone. I'm sorry for being a little late. My last class ran just a little bit over, but I'm here now. We've now have ostensibly 46 people in our class. 46. Oh, that's a big number. More coming in as we speak. Let me send an email. The 46th person is in the process of enrolling, and I need to send her an actual link. So let me do that right quick while I'm waiting for you guys to all shuffle in. Let me kill this just for a second. I'm going to go back here and go here. Click on that. This is today. Copy the invitation. And I'm going to narrate it because I'm old and that's what keeps us from forgetting what we were doing. That, eating our oatmeal and not, and our fiber, getting our fiber is very important, evidently. I'm making fun of myself. I'm not really that bad yet, but I'm working on it. I like to eat really spicy food, so I'm probably going to have to migrate to oatmeal soon enough. Yay, I'm a whole 4 minutes late. Isn't that just awesome, awesome, awesome? People are still coming in. Let me see. I don't want that class. I want this email. Let me go back to my little gray shack to my, I definitely work in stream of consciousness, as you can tell.
Professor?
Yes.
Have you posted the access code for my lab on Canvas yet?
No, and you're not supposed to use an access code. Access code is for accessing it from outside of Canvas. My course is integrated. And if you did it the other way, the systems are not that smart. They don't know better. They'll let you do it. And then I would never see your grades. So you've got to go through the My Lab and Mastering link on our Canvas page to get to your mastering.
I click on that, but it prompts me to put in an access code for the course.
Okay, now there's also a code, not for the course. It is called an access code, and that's the one that comes with your book. If you bought a new book, they either emailed you one or gave it to you in the book itself. That's what you're needing.
Right now I'm on the temporary access for like the 14 days until I get my student aid.
Then you're supposed to just be able to sign up, create a new username and password, and it usually gives you the 14 days. Did you make an account yet? Have you tried that?
Yeah, I've had an account already, and it gave me the 14 days access, but it keeps on telling me to put in a proctor code or a course code.
Yeah, okay, so don't ever go through the internet. Always go through Canvas. So whenever it asks for an instructor code or a proctor code or something like that, that's almost always because you've accidentally slipped outside of the Canvas system. So check that. If you still have problems, what you're going to need to do is contact My Lab and Mastering. So look for a contact number on their website and do that. If you can't get anything done by tomorrow, send me an email and I will set up a Zoom meeting for you and we'll go over it in real time.
All right, I'll try it again later on.
Okay, let me send this message to my student right quick. Man, it's so hard to type when I'm rushing. Well, all of a sudden my fingers have become plastic. Okay, now I've got that taken care of. Sorry about that, everyone. Still got 2 more people trying to get in. All right, everybody's here. So what student was telling me they're having problems? Is that you, Mika?
Yeah, Micah.
Micah, sorry about that, bud. And I apologize in advance. I'm horrible with names. Luckily, with Zoom, I've got it written up there in front. But I'm horrible with names, and I really am bad at pronouncing people's names often. In fact, I sometimes accidentally slip into like a Midwestern accent when I'm trying to do an impression of a friend I met from Puerto Rico. So it tells you I might be functionally mentally limited. All All right, we got 42 of the 45. I'm feeling that's of the 46. I'm feeling that's pretty good. Does anybody have any questions about what we did so far? All I did was really talk about scientific notation, converting units, mostly just the converting units. I think everybody already knew both of those things, but those are really critical. I told my students just last class, which is astronomy, a non-mathematical course, I told them specifically that converting units in 1988, I was a lifeguard at a nice resort in Kerala, and I was a lifeguard and did various other things. Well, they had some pool problems, and I'm always a guy that likes problems and trying to solve them. So I grabbed the manual from the test kit and read it overnight. It's only, it's not very long. It's like 20 some pages or something. But I realized everything they do is just unit conversion. So immediately, like my first week on the job, I went from making $7.50 an hour, which was really good in 88. 88, I think $4.50 an hour was the minimum wage, and I was making $7.50, and they bumped it up to I think $10.50 an hour because I became the pool manager and the lifeguard, all because I knew how to use unit conversions. So unit conversions are really amazingly helpful. A lot of engineering work is linear, which means it's just a unit conversion as well. Sometimes it's a little more complicated where you have to do mx plus b as opposed to just a unit conversion. But the vast majority of stuff I did in structural and wastewater engineering is all linear. So I didn't have much difficulty making that migration from physics to engineering. I just basically found a couple of the major textbooks that are so appreciated in engineering and read them and learned how to do structures, learned how to do foundation design, learned how to do wind analysis from a publication. So it's pretty cool what you can pull off with a little bit of physics knowledge. Does anyone have any questions on any of that stuff? I think not, but maybe you do. Okay, someone said the minute mastering is up, but didn't see the syllabus. Okay, I probably put it up, but didn't publish it. There's a button I have to push every time. And sometimes I even push it and it takes a long time to register. So I click it again. And then I think, okay, well, I did it. Well, what happened is it was such a delay that it turned on. And then at the second click, I turned it off. So I will check that right after class. That should be visible. Everything's been made. I've already found a couple typos in it, so I'll be making a change to it. What you'll see is there will be a module called helpful links or helpful documents and links, something like that. And in there will be the syllabus, and there will also be links to other courses, like Khan Academy and that MIT Open Courseware course, stuff like that, that can help you better learn the material as we go along. So I definitely recommend you spend an hour just playing with all the links, looking at all the things I give you, and that could be helpful. In general, if you're a savant or you're just awesome and know your physics really well, you should be able to just jump right in, read the material. Some people are even bright enough to just watch my lectures, watch a few extra videos, say on my YouTube channel, and do all the homework without ever reading their book. I don't recommend that. You're losing a lot of knowledge. You're losing a lot of at least trivia, but actually real world applications that are super helpful and make you not look like a goober. So definitely try learning to read the book. You should figure out how long you can read the most boring book you've ever seen in your life. See how long you can read without losing attention span. If it's literally a minute or 2 minutes, that's okay. That's pretty normal. You want to time yourself doing that, and then from there, for probably the next 10 to 20 readings, you want to only read that long. And then the next time, add either 10% or a minute, whichever's longer, to your reading time, and do that for another 10 to 20 cycles. And then do it again, add another 1 minute or 10%, whichever's larger, until you can get, ideally, as a calculus-based physics student that's going to major in engineering, physics, chemistry, biology, pre-med, any of those type things. If you want to really be successful, you should shoot for being able to read for 2.5 hours by itself without losing focus. So keep doing that gradual increasing. Try to read interactively. Try to predict what the author is saying. If the author makes a claim, try to take that claim and think of a supporting example, and then try to think of a contradicting example. And by doing that, your brain's engaging. You can take a break from that sentence for a second and think that out, and then go back to the sentence and read on. And if you can't figure out that there's not a contradiction for what the instructor said or what the author said and what you're thinking of your example, then you need to do some Google research and just Google some things and find out if you know why, what was a little nuance, or two, maybe you misunderstood it and it's time after you've done all that research, if you still don't understand it, that's when you want to ask me. So ideally, I would have you all read the sections that I cover before I cover them, and then you might have to do a cursory read again after I cover them and then do the homework. You'll see my homeworks include concept questions, which is a small percentage of your grade, and homework questions, which is a bigger percentage, but still fairly small. But basically, I want you guys to be able to read and use your reading to learn how to do something new. And you can't do that unless you really get honed in on reading skills, reading interactively, trying to predict what he's going to tell you about in the future, he or she or whatever. So keep that in mind. Someone said the mastering's up for me. Oh yeah, the syllabus already answered that question. The other one said, can we buy my lab and mastering separately if we bought a used book already? Yes, you can. And here's the sad part. My lab and mastering, the last time I checked, they bundled it with an e-text, and therefore you pay on the order of $90, which is what the e-text costs with the with the software, or with the access to the software. So you might find that you ended up biting yourself in the rear, but unless you bought an older version of the textbook, then you probably still save some money. So yeah, if you go to the website, either through Canvas or not, you should be able to buy access to, and I think, like I said, they automatically link it to the ebook as well as the homework, but it should be around 75 to $100. I would say you buy, if you've never had a physics course and you're afraid that you might actually fail, the 24-month might be a smarter route, but I don't think students should be failing any classes ever. And if you think you can do this without failing, I'd say 12 months should be plenty. You just got to make sure it's going to be scheduled either the summer or the fall for the next course. And it is. I always have a 242 in the summer, and I always have a 242 in the fall. So you shouldn't be able to, or shouldn't miss a class. It just might not fit with your schedule that well, and you'll have to force yourself to take it to keep from losing. So I would say, generally speaking, for all my students, 12-month plan is plenty good, and you save yourself a little money. But if there's any really self-doubt, you might want to do the 24-month plans in case something happens. Heck, we're dealing with a quarantine. That's hard enough environment to learn in. You might actually get sick. Something bad could happen. But it's all up to you beyond that. Any other questions? And you can ask them too. You don't have to just chat them. I do appreciate you chatting them. Sometimes I miss that while I'm talking though. All right. Well, it looks like we're pretty good to go. So what I want to do is we're going to finish up chapter 1 today. I generally do a chapter a week, as I mentioned in the syllabus, which evidently people can't see yet. So that's kind of moot for me to say it. But I'll give you a little idea what the scientific method is. And there's not the scientific method. For instance, people say, you make a hypothesis, you observe, you predict, blah, blah, blah. And that was really literally a scientific method that some publishers put together, asking a bunch of people that taught science. And it's not necessarily the way science is done. So what I like to do is try to explain science and the difference between a theory, a law, and a hypothesis this way. So what I see science as is walking through life, you see something occur. You then want to understand what that is. Why did that thing occur? Why did a leaf fall from a tree at this particular time? That kind of thing, right? That's an observation. Sometimes you see an observation that contradicts what we see in everyday life, and you want to investigate that. Sometimes you just use a picture in your head and say, I don't like the way people are thinking about this. I'm going to do this. That's what Einstein did. They say one of the marks of a genius is supposed to be being able to hit a target that no one else can hit. But the real mark of genius is seeing a target that no one saw existing and then not only hitting it, but nailing it, right? That's what Einstein did. Einstein looked at Maxwell's equations, which poor Maxwell had put together, and literally died without the respect of his peers because they didn't know calculus, vector calculus. So a lot of people just thought he was a highbrow mathematician that didn't really do much. And he died at a young age of cancer of the stomach. So he died without the respect of his peers. By the time Einstein comes along, everybody realized, oh crap, this guy Maxwell was the bomb. You know, he understood atoms. He was the first person to predict what the rings of Saturn were, all sorts of wonderful things. And pretty much we can do 99.99 probably percent of all the electrical engineering stuff we need to do, we can do with what Maxwell taught us. So by the time Einstein comes along, he realizes, like everybody else, that Maxwell's the bomb. But he starts looking at Maxwell's equations and realizes, hey, this creates a wave equation, and if I'm moving at some particular speed, that wave equation doesn't change. And from that, he saw all these weird anomalies coming into place. Basically, he saw self-contradictory paradoxes. You know, a paradox is something where two valid theories predict two very different outcomes, and he saw a lot of that. And physics doesn't accept paradoxes. Paradoxes are not acceptable. If we have a paradox, that means there's something in science or physics we don't understand as well as we need. So he saw these paradoxes, and the only way he figured out to fix it is that the speed of light is a constant independent of the velocity of the source and independent of the observer and its velocity. When he did that, that made Maxwell's equations work again as well. But it also made for some weird things, like he predicted the length contraction and time dilation and an apparent increase in mass the faster you go, and addition of velocity is weird. So in that sense, he didn't see an observation of something that needed to be fixed as an actual experimental thing. He started at the very first part, which was make a hypothesis, okay? Bacon taught us don't do that. Bacon said you should never make a hypothesis until you've seen a lot of data. And there's some correctness to that. You're more compelled if you make a hypothesis before having a really good understanding of the data. You're more likely to protect your hypothesis and allow yourself to do some what we call self-confirmation, which is confirmation bias. So there's pluses and minuses to both sides. But what I see science as is you make an observation. Okay, it's going to be a little three-part cycle, if you will. So you make an observation. From that observation, you make a hypothesis. Now, the hypothesis might be something small like, hey, I saw this little kid throw a ball, and it looked like when the kid threw the ball with a straight arm, it looked like it completed an arc whose radius, it's an arc of a circle, whose radius is the height of the person's hand when he threw it. So then he could go and say, okay, well, that's my hypothesis. Balls leave hands in the arc of a circle whose radius is the height of the hand when it was removed. And of course, it starts off at whatever angle it's released, so on and so forth. And you do a few observations and you find it's pretty close, but there's these little errors, like it's not exactly a circle. In fact, we now know it's a parabola. But that would be a hypothesis. That's actually not only a hypothesis, that's a model that allows us to make predictions. So we go from observation to hypothesizing, and then with that hypothesis, we make a prediction. So there's the third part of the little triangle. So we make a prediction. Once we make that prediction, then we go back and observe again. So it's this little triangle, ding, 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 ding. So we go observation, and it doesn't, like I said, you don't have to start at observation. That's just a typical way of doing it. You make an observation, you make a hypothesis / model. The model / hypothesis makes a prediction. The prediction then can be tested with an observation, and then you keep repeating that over and over and over and over and over again. Once that hypothesis has been really fleshed out so much that you've got a really deep understanding, something more than just saying it's an arc of a circle, right? Then you continue to predict and continue to observe and continue to predict and continue to observe. If you ever find a contradiction between your prediction and observation, you either have to throw that whole thing out or tweak it to make it work better. And you keep doing that over and over and over. Once you've gotten rid of all those little parts that give you contradictions, maybe you get 100,000 verifications of every prediction you make. Maybe you get 2 million of them, whatever. Once you get a certain number, a really large number, that's slowly becoming no longer a hypothesis, but a theory. Okay, so theory is a strong word in the sciences, and scientists still don't use it as purely as they're supposed to, because they slip back and forth between scientist language and common language, scientist language and common language. But a theory is supposed to be a strong word. It should never be followed by just a or that's just a theory type thing, right? So theory is something that is a hypothesis. It's got a deep paradigm, a structure to it. It's made millions of predictions and never once been found to be wrong. That is a theory, but the nature of a theory, if it's really science as opposed to dogma, is it only takes one observation thereafter to completely debunk it. One well done observation that someone can replicate. And then that theory is now in the dustbin or has to be tweaked again, like we've said, and starts anew. In the case, for instance, of of Newton's gravity, it worked for a long time. And we don't call it wrong necessarily. We just call it incomplete because it still covers so many things. We could go to the moon without general relativity. You know, we can get to Mars and other planets without general relativity. There are some things that we use general and special relativity for to make sure some of our instruments work properly, but we wouldn't be that far off if we just ignored Einstein completely and did Newton. We could still do a lot of what we had done before. So Newton's theory is still a theory. We just know it has limitations. That's what normally happens to a theory. Bohr comes along and introduces this thing called the correspondence principle, and I think it's wonderful. And the correspondence principle says, hey, if you've got this theory that works really well in this broad scope of applications, then any new theory that you're going to replace that one with better explain those other ones just like it did. Okay, and that's what Newton's special relativity, or excuse me, Einstein's special relativity and Einstein's general relativity did. They come in and, you know, instead of saying like Galilean relativity, which is related to Newtonian relativity, that the velocity of A as seen by C is equal to the velocity of A as seen by B plus the velocity of B as seen by C. That's the Galilean, and we'll get to that when we get to relativity. You'll know that equation, but basically the velocity you're calculating is AC, that's the subscript. The two velocities you're using are A something and something C. Notice the AC matches, the outer symbols, the outer prefixes match. Then the two middle prefixes have to match, or suffixes have to match as well. So B and B is fine, or Q and Q would be fine. That's general. That's Galilean's relativity, how velocities add. Well, it turns out when you do special relativity, that same part of the formula is in there, but below it is a 1 plus the product of those two velocities divided by the square of the speed of light. That number, 1 plus that thing is really, really teeny for all the velocities we use in everyday life. That's why we never noticed it before, but that's a perfect example. Let me show you my document cam real quick, just to give you an idea of that. So what we're saying in Galilean relativity is that the velocity of object A as seen by object C is equal to the velocity of object A as seen by anything, really. I'm going to put a blank there for right now, plus the velocity as seen by of anything as seen by C. See how the A and C match the A and C here? Now, all that's critical is this middle thing matches. So I had said it was going to be B, and that's fine. You can put B in there. I could have put Q in there and Q there, or I might have to string them all together. And this is actually a vector equation too. That works great, right? The only thing you got to make sure is these two match this, and then these two match this and this. If you got that, you're golden. Okay. Plus, there's this other rule. Sometimes you don't know VBC. Maybe you know VCB, the velocity of C is seen by B. Well, the general rule for that is Vij is equal to the negative of Vji. So sometimes this plus becomes a subtraction. That's it. Again, I'm being very generic here, and you might not feel a lot of structure, but what I'm saying here is, like, let's say the velocity of a baseball pitch, which we call A, as seen on the side of the road. So velocity P from side of the road is equal to the velocity of the pitch as seen by the flatbed truck they're on. So a truck is moving at 60 miles per hour, and you've got a professional baseball pitcher standing on the flatbed truck, and he's throwing in the same direction the truck's going. The truck's moving at 60 miles per hour. The pitcher throws at 100 miles per hour. Okay, so this is the velocity of the pitch with respect to the truck, which is positive 60 miles per hour. Then you'd say, okay, well, this middle one has to match. So I'm going to say the velocity of the truck as seen by the road, and that one's the positive 60 miles per hour. This one's the positive 100 miles per hour. And like you expect, if you're watching this truck go by you, you believe the truck is moving at 60 miles per hour, and then you see this jerk throwing a ball in your direction, which is the same direction the truck's going. Well, he's throwing it 100 miles per hour with respect to the truck, so you expect the result to be 160 miles per hour. Does that make sense to everyone? Okay, so that's exactly what's happening. That's the Galilean Law of Relativity. And that's how velocities add. Now, if you knew the velocity, say the truck driver said, well, I saw you coming to me at 60 miles per hour. Sorry, I went into my redneck talk. I don't know why. I actually know nothing but city folkers that drive Mack truck. But anyways, if I knew the velocity of the road with respect to the truck, then I could switch this because I'd have RT instead of TR, and I'd just do that by changing the sign to minus. Okay, but to the truck driver, everybody has to agree that the forward for the truck is the plus direction. So what the truck driver is reporting is that you're coming at them at negative 60 miles per hour. Again, I go with my hick accent that I have from here in Currituck. All right. Now, here's the cool part. This shows you what I mean by the correspondence principle. When Einstein comes along, Einstein says the velocity of the pitch with respect to the road is equal to the velocity of the pitch with respect to the truck plus the velocity of the truck with respect to the road. But they all got to be parallel unless you use a more complicated formula. So what I'm going to do is take off the vectorness of it and just assume they're all in the same x direction. Now, what Einstein added to it was VPT times VTR over the square of the speed of light. And the speed of light, get this, you're going to have to put these velocities not in miles per hour, but in meters per second. And it turns out the speed of light is 300 million meters per second. So you can imagine 60 miles per hour. Let me do real quick to remind you. I think we did that last time. I'll let you know what 60 miles per hour was in meters per second. Again, I'm going to type it up and say 60 units, miles per hour, and I'm going to add to it 0 meters per second. And I'm going to say plus, and that's 28.64. So 60 mph equals 28.6 meters per second. So maybe 100 would be what, 56 plus 2/10, which would be 5. So maybe 57. So 57 meters per second plus 28 meters per second is what you get for this top. So 55 plus 28 would be 77 or 75 plus that'd be 68 meters per second. So you'd expect 68 meters per second coming out of that. And that would be consistent with the 160 miles per hour. But when you take the 58, the 55 and the 28 and stick them right there, you can see this term is going to become essentially 0. Because, yeah, 28 times 55 is a big number, but it's nothing compared to 3 with 8 zeros behind it squared. So this is a perfect example how Einstein's theory obeys the correspondence principle that Bohr put ahead, which says, hey, this better reduce to that in the cases where this works. And it does, because you take the limit as this approaches 0, you get that, which is identical to that. Does that make sense to everyone? Okay, so that's the correspondence principle, and I think that's a key part of science. Another thing of science that's important, but not really, there's no real physical reason to believe it, except we just do. If we ever find a case where we don't, then we're going to stop using it, but so far we have it, and that's called Occam's razor. That's spelled Occam, O-C-C-A-M. That's Occam's razor. He was actually a monk. And his idea was if you find 2 hypotheses that are equally good at predicting what nature will do, then you can probably assume the one with the least number of assumptions. In other words, an assumption would be that I believe there's fairies, and fairies make sure the laws of physics are obeyed. And then the other hypothesis would be, say, the laws of physics. If you exist, if you argue that there's fairies that make things appear as if there's a laws of physics are working, and then you just compare it to the laws of physics, the fairies required more assumptions that you were not sure about. Therefore, Occam's razor would say we should probably throw the fairies out. Does that make sense? So that's Occam's razor. And again, we don't really have any reason for believing it. It just so far has worked out really well. So when we looked at the model of the solar system in the early parts, what we call the Ptolemaic model, that had our sun right here. Okay. And then what it had was Mercury orbiting it. But that didn't explain some of the stuff we saw. Then it had, of course, Venus orbiting just outside that. So this was Mercury, and this is Venus. And then we had, say, the Earth orbiting outside of it, like so. But then we had Jupiter, which was on a epicycle. So it had an orbit, but it had the center of its orbit on another orbit. And this was where Jupiter was. And that was the only way we could explain why sometimes, or usually, the planets make a faster speed compared to the background stars, but every now and then it gets brighter. The planets will get brighter and then start going backwards. To explain that, they put a loop on a loop. So this is sort of the reference they were making in A Bug's Life when he says, yeah, you remember his tunnel within a tunnel idea? They're talking about the guy that kept screwing up things by his inventive and creative nature. This is the Ptolemaic model. And not only that, you had to make the Venus, in order to make the evidence work, you couldn't let Venus just be on an orbit. Venus had to be on an epicycle too, and that center of that epicycle had to stay on a line connecting the center of the Earth and the center of the sun, and Mercury had to do the same thing with a smaller circle, right? So this Ptolemaic model assumes that this epicycle exists, this deferent exists, this epicycle exists, this deferent exists, this line exists for some reason, this epicycle exists, and this deferent exists. There's a lot of assumptions that we can't verify. When Copernicus introduced his heliocentric model, excuse me, I should have put Earth here. I don't know why I did that. This is supposed to be Earth and this is supposed to be Sun. I started with the wrong one. With this being the Earth here and this being the Sun here, all that's the Ptolemaic model. Sorry about that. That's kind of a bad thing I just did. I apologize horribly. That's the Ptolemaic model. When Copernicus comes in and says we have a heliocentric universe, and he says that he still claims that the orbits are circles. He only claims that Mercury follows a circle, Venus follows a circle, Earth follows a circle, so does Jupiter, so does well, he didn't know about anything other than Saturn. So Saturn followed a circle as well. And the data that Brahe gave us said that this model was about the same accuracy as this model. So Occam's razor would have required us to throw this one away, because I had to assume that an epicycle exists and a deferent, an epicycle and the deferent, an epicycle and the deferent, and this line all existed. And I don't know that that really is so. Whereas this one, I just have an orbit, an orbit, an orbit, an orbit. That's it. So Occam's razor would say Copernicus is right. Now, he turned out to be friggin' wrong, because he was still held on Aristotle's idea of everything in the heavens being perfect circles and nothing changing. So nothing ever sped up or slowed down. So it turned out to be bad. So Brahe's data actually comes along and makes it so good, makes such good data that we have to throw this model out and come up with Kepler's model, in which the orbits are ellipses, and they actually speed up and slow down while in that ellipse. So that's an overview of sort of the scientific process. It's let's stop sharing the document right now. So it has this structure. where it's cyclic in nature and never, ever, 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 ever stops. It always asks more questions. You're constantly observing, taking your hypothesis and making a prediction, taking that prediction and testing it against observation, predicting another hypothesis or predicting another thing, observing, and you keep doing that. Once you've gone through that cycle hundreds of thousands of times, or maybe even millions of times in the case of special relativity, and never once been found wrong, then your hypothesis slowly migrates to a theory. Okay. And then laws, law could be interchanged with the word theory, but they actually have historical names like Charles's law or Boyle's law being the scuba diver's law. That is in some sense a law in that everybody has always noticed that pressure and volume are inversely related. That means if the pressure goes up, the volume that is subjected to it will go down. So in that sense, you could call that a law. You could call that a fact. If you compress by increasing the pressure, a volume of gas, its volume will decrease. So that's what laws are. You can think of them as single observations that explain the way something behaved, but you'll also hear them on occasion be referred to as what we normally call a theory based on what I just told you. So you can talk about Einstein's theory of general relativity, or you can talk about Einstein's law of general relativity in that second sense. But generally what we modern physicists and scientists try to do is use laws for some observational fact that led us to some deeper meaning. Charles's law, Dalton's law, Boyle's law, Gay-Lussac's law, Avogadro's law, all those things, okay? Now, outside of that, that's mainly for you to understand that when people say just a theory or use a diminutive adjective in front of the word theory or even after it, if such a word exists, then you can know they're using the wrong definition of theory, and that's something you should keep in mind. Now that we've sort of given you that background of what the scientific process is, I want you to use that scientific process when you're trying to solve physics problems too. There's inevitably going to come some mathematics that you've never seen before that you've got to do. And if you've been sort of experienced with your math throughout algebra, pre-calculus, and even calculus, then you've probably got some ideas of some of the things you can try. So what you want to do is implement the scientific method on that too. Solve the problem the way you think, check the answer in the back of the book. If the answer in the back of the book or on the homework system isn't right, then say, well, let me try that other option. And then make a note of that, because in the future, you'll need to know how to solve that type of problem again, and you'll have to know how to do that mathematical operation again. So we should use the scientific method not just to conduct science, but to conduct everyday life. You know, if you come home on your wife's birthday and you brought her a really kick-butt dishwasher, she might not be all that happy about that. That's not her damn job, right? It's no more her job than it's my job, all right? Than it is my job. So if I did that, I would take the scientific method and say, evidently, when I get my wife something that admittedly was supposed to make her life better because she does way more dishwashing than I do, I just got to fight from that. Okay, so maybe I'm going to use that as a hypothesis that no more am I going to buy stuff for mutual tasks in our home that her and I are equally capable of doing. So that's a scientific method applied to a relationship. You can apply it to driving. I discovered that my new car has a device that if I let go of the steering wheel or if I swerve over the right-hand line, it pulls my steering wheel back, right? So my hypothesis was I'm going to drive a little bit with no hands on the wheel, just see what happens. And I almost made it. Then they actually crossed the line and there was a guardrail coming, and luckily I realized what was going on, that it sort of forgot for a second, so I pulled it back. But that made me get another hypothesis, which is maybe I shouldn't trust the car to drive, right? It's not a self-driving car. It's just a car that helps me from being an idiot sometimes, but it doesn't always work. In fact, one day I was riding around and there was this old man walking on the side of the road, and I was in one of his back roads. It's very narrow, a ditch on each side back in Pungo. And I swerved to miss the guy. Well, the car's like, hey, man, you just rode over the dash yellow line and yanked me back towards the old man. I could have killed him, right? So what I discovered is if I put a turn signal on really quickly just before I get to somebody on the side of the road, then my steering wheel don't yank itself back and I have less chance of killing somebody. So I use scientific method in everything. I use it when I go on a trip. I look up on MapQuest or something like that. I'll look up how many miles it is to such and such a place. I make a hypothesis about how many average miles per hour I'm going. I've been doing this for decades because I'm a nerd, and I've discovered that usually on interstate trips, you know, say from here to Florida or here to Georgia or here to Memphis, Tennessee, I average usually around 42 miles per hour. So I immediately take distance equals velocity times time. And I use that to solve for the time. I divide the distance to, say, Memphis by the 42 miles per hour that I assume. And then I say, well, it should take me this long. And then I keep two clocks. I keep a clock memorizing when we left and cutting out each time we stopped to take a potty break, to eat a meal or something like that. And then I know another one to keep up the total time so I can have a better estimate of how long or how what my average speed is, taking into account stops. I literally do that with every trip, and I just work it in my head because I love doing multiplication and division in my head. It keeps me from growing into my Alzheimer's proclivity. So I do that, and lo and behold, I get this feedback data instantly. I also do things like tracking my miles per gallon. So I keep track of how many miles I drove, and then how much gas I had in it initially. You know, I fill it up to the rim basically, and then when I go to fill up, I see how many gallons it takes to fill it up to the rim again. That's how many gallons I've used. I take the miles that I have now minus the miles that I had with the last time I filled it up, and that gives me miles per gallon. I compare it to what the computer's telling me, and I find that the computer does a pretty good job. Sometimes I find the computer's doing a horrible job. And I look at it a little closer, and I realized, well, yeah, I did sit outside the school when my daughter was at a dance. I sat out there with the car running for 2.5 hours. Yeah, I didn't get very many miles per gallon there. So that's kind of neat too, because that says, hey, yeah, it's probably not very efficient to sit in the car in a parking lot with a car running. I keep seeing Micah's face smiling, and I'm thinking I'm telling really good jokes because he's laughing. That's cracking me up. Let me switch to someone else's face. All right. So I don't think I'm so entertaining. All right. So that's our scientific method. But when we go to use science, we all got to agree on what we're reporting. To make something agree with what we're reporting, we all have to have the same system of measurements. And that's where we come into one, measurements and uncertainty, and two, what units are we going to use? So it turns out whenever you grab, say, a meter stick or a ruler or something like that, maybe you have one like this, what you see is, hey, this top thing goes from 0 to 25, this top scale does, right? And then I see that the numbers from 0 to 1, say, there's a bunch of little spaces in there. Actually, I keep doing the wrong side. There's a bunch of little spaces in there, so I count the individual spaces, not the lines, I count the spaces. And I see there's 10 spaces between 0 and 1. So I say, oh, well, each one of them must be 1/10 of the way. So I now know that those individual marks, the smaller ones, are actually tenths of a way. And I see that the fifth one is always a little longer, and it's usually a little shorter than the whole number one. So in this ruler, it's not the case. They just put the whole number on there. So that's a good indicator. So I know that each of those little marks is 1/10 of 1 unit. Well, I happen to know that a centimeter is about the width of a human fingernail. So looking at this, I'm thinking, oh, these things are about the width of a human fingernail. So I'm thinking this is a centimeter scale. It don't say it. You know, this is a crappy ruler. It don't say what the unit is. This one down here, I know is in, oh crap, that sucker's in 16ths, right? That bottom scale is 0 to 1. That looks like an inch to me. So I can confirm, because there's 2.54 centimeters in an inch exactly, I can confirm that these are in fact centimeters across the top. And I immediately think how stupid we were for using a base 16 for the non-metric system, i.e. for the British system, because it's crap, right? You gotta first take and divide 1 by eighths, or first by 2s to get a half, then by quarters, and then by half of quarters, which is an eighth, and then by half of an eighth, which is a 16th. And it's just a nightmare. So we use the metric system. But what you realize is if you're measuring something that has a really clearly defined end, let's say this is pretty good because it's fairly square, I wouldn't want to measure if your meter stick goes all the way to 0 and that's the end, say, I wouldn't want to measure from the end, specifically because if it's the end of the meter stick, I might have gnawed the end off, right? Or a dog might have, or you just got it scratched up every time. So that's not a good ruler to use. In fact, most good rulers usually have some area just off the edge, a little bit from the end, so that you always know exactly where the 0 is. If you don't have such a ruler, then what you want to do is say maybe measure it from the 1 centimeter mark instead of from the 2 centimeter mark. You just got to remember to subtract a centimeter out of it. Okay. But if I do measure something that way, let's say I measure the length of this thing, I could use the 0 because this does actually go to 0. And then it clearly shows me this end. It's a fairly straight line. I got a rounded corner. That makes it a little difficult. So I can't get that good of an estimate, but I can still estimate it pretty well. And when I measure this, it says I'm putting it right at the 0 and just to the edge of the metal, not to the little thing that's sticking out. This says it's right at 7.4. I'm going to call that 7.44. 7.44 centimeters. Now, what I wanted you to notice about this, if I can ever remember which way it is, the screen's flipped back and forth, so that's why I'm always doing the wrong thing. Yeah, like I did now, I got it on 25. So 7.44. Notice this thing's only marked to the nearest tenth. These individual marks in here are 7.1, 7.2, 7.3, 7.4, 7.5 is the tall one, and then 7.6, 7.8, 7, 7.8, 7.9, and then I'm up to 10 tenths, which is the next one, which is 8 centimeters. So I said this was 7.44. You should always be able to get one extra digit beyond the markings. I might not know whether a measurement is 7.4 or 7.3. But I certainly know the difference between 7.1 and 7.4. And I can tell there's a difference between 7.4 and 7.5. So it's not necessarily an error of 0.1. It might be an error of 0.2, because sometimes I can tell it's definitely not 0.5 and I can call it 7.44. But sometimes I can't even make that sense out. So I have to go with something like 7.44 plus or minus 0.2. So that's how we record numbers in science, is every number has an uncertainty. No matter how good a device you're using, it's going to have some uncertainty, because even if we had another scale that was what we call a vernier scale, where we actually, damn it, this is hard, where we actually could estimate that next decimal place, but more consistently, then I would still have a problem in that there's another decimal place I should fill out. And if I got a vernier scale, I could do that maybe. But there's some limit, because eventually I'd run into getting such a small size that I'm looking at the individual edge of atoms in a lattice, and those atoms are going like that, right? And if they're doing that, they're causing uncertainty. So no matter what, you're always going to have uncertainty. The big deal is, though, is 1, admitting you have uncertainty, 2, quantifying that uncertainty, and 3, reporting that uncertainty. Okay, so let me show you something on my document cam real quick. So I just measured that the width of this tape measure, which says it's 3 inches, by the way. It says it's exactly 3 inches. That's what it said on the doohickey. See the 3 inches? Wee, fancy. What I found that to be was 7.44 centimeters. Now, if this thing would have been all weird shaped, I might have had to say an even bigger error than I'm going to say. What I'm going to say is this quantity called X bar. That's my best estimate. It normally means average. So what I'm really meaning is I'm going to take that measurement 10 times with the same measurement device, or 5 times, and take the average, right? Because sometimes maybe I'm looking at it at this angle. Sometimes I'm looking at that angle. Sometimes I'm making careless mistakes, all sorts of stuff. But I take an average, and that would give me that. But then I'd say, well, I want to report the number as X is equal to 7.44 plus or minus 0.2 centimeters. That's me reporting not only the number, but how precisely I measured it. And in fact, this little quantity right here is called the uncertainty. So what X is X bar plus or minus sigma x, which is the uncertainty. Okay. Sometimes people will use this notation, x bracket plus or minus sigma x, and that's acceptable as well. Either one will do, but the main thing is, remember, when you're in a lab situation, you're supposed to make a measurement several times, take an average. That's what goes on this part. You should use your device as far as you can. If it's a digital readout, you can't make up an extra digit. You're just going to have to write down the digits it has. But in that case, you know the error is at least 1 in that last decimal place when you're dealing with digital things. Does that make sense to you guys? Like if a multimeter says it's 4.26 volts, then you know it's 4.26 plus or minus 0.01 volts. So that's what you do when it's digital. The big deal is, though, if I now take this number and I want to find an estimate, say, of the actual area, let's say I'm going to treat this object as an actual square. It's clearly not a square, but that's okay. You know, we're approximating it as a square. I'm going to say it's this square right here, and I'm going to try to estimate to the center of that, even though it's a little higher over here, because that's a rough estimate of what the surface area would be. Obviously, it's way to poop off because this bulges out. It's not a square. But I could maybe take the longest part from here to here and estimate that to be the size, and maybe that extra bit that I'm assuming there can count for the extra bit that I'm cutting out here. So that's an approximation. I'd say then the area, our best estimate of the area, would be our best estimate of the x times their best estimate of the y. Does that make sense? So let's pretend I did a bunch of measurements and I tried to really measure what that is. Let me kill this for a second and go back to my camera, my webcam. So I already measured this dimension right here and said it was 7.44. And let's pretend I actually took all the measurements, a bunch of them and stuff, but we're not doing it. And now I'm going to take, to compensate for this little, to compensate for this little extra bit that's not counted in my square from here to here, I'm going to add an extra bit from here to here. So I'm going to assume it's a square that's about this tall. You can already see that I'm starting to deal with an error because I'm measuring way across the distance and just estimating where that edge is. I could actually do it a little better by measuring it right at the edge, but I wanted to show you what could happen. So I'm going to measure this. I'm estimating roughly the edge is right about there. That looks pretty good to me. Yeah, right about there. And then this one seems to be 7.72. So I'm going to call y, go back to my document cam now. I'm going to say y is equal to 7.72. Now that one was kind of messy because I was measuring from here to here and estimating roughly where this edge was just by looking at it. I was being stupid. It would be much smarter to just obviously measure right across here, but I wanted you to understand what I meant when I say it's not easy to measure some things. Maybe you can't get to this other side and measure it like that. And in fact, you can see a little error already. I estimated it to be 7.72, and this is looking more like 7.6 something, but that's okay. I'm going to take that into account by realizing that the error there was more than the 0.2 that I had before. I'm going to suggest that error is probably plus or minus 0.03. Oh, there's supposed to be a 0 here. I don't know why I didn't write it. So everybody sort of record that 0 in there. I think I said it right, but I never wrote it. Remember, that uncertainty lines up with the last decimal place. That's a key whenever you report numbers. So let me rewrite that. That's supposed to be 7.44 plus or minus 0.02 centimeters. So I'm going to mark through that. That's the way you actually are supposed to do data in a real lab setting. You write in pen so you can't erase stuff, and you don't blur it out when you have a screw up. You want to be honest with everybody that's reading it and say, hey, this is me being an idiot. And they want to see exactly what it is so they can tell whether you're fudging or not. So in this case, I want to say 7.72 plus or minus 0.0. I think 3 is good enough. Some people might argue 4, but I'm going to say like that, and I'm going to say that's centimeters. So what I then do is I say, okay, well, the A is supposed to be x bar times y bar. Well, that means 7.44 centimeters times 7.72 centimeters. And when I do that calculation, y'all can do it with me. That would be awesome. So make sure I don't make mistakes. 7.44 times 7.72. I get 57.4368. I'm going to write all the digits for instructive purpose here. 57.4368. Centimeter times a centimeter is a centimeter squared. Now, the problem is I don't know where to round this. I had, measured both of them to the nearest hundredth of a centimeter, but this one had some error in it and this one had some error in it, and the errors were different. Maybe I assume it's in the second decimal place, but that doesn't even have the same unit, so I don't think that's right. So one person might actually suggest maybe the uncertainty is what comes from half. Remember, certainties are always plus or minus. So it's like an equal amount higher and equal amount lower. So what I might do is say, let's say A big is equal to X plus sigma X, not plus or minus, just plus, times Y plus sigma Y. That's an approximation of the biggest possible area we should have, right? So when I do that, I'm going to do 7.46. See, I added the 0.02. 7.46 times 7.75. And I get 57.815 centimeters squared. So that's the biggest possible thing I think would be reasonable. The smallest one would be A small, which I'm going to say is X minus sigma X times Y minus sigma Y. Does everybody understand why I'm doing pluses and minus there? What I'm saying by putting that plus or minus 0.02 is the absolute smallest I really expect this to be would be 7.42. The absolute biggest is 7.74 or 46. So now I'm going to do that. I'm going to do 7.42 times the other one would be 7.70. And in that case, I get 57.134 centimeters squared. So I see the difference in these two. Biggest minus smallest, the delta is just going to be the top number minus the bottom number. And I get 0.681, 0.681 square centimeters. Okay, well, remember that's the total, and I only want half. I want to see my estimate is dead center, so I'm going to cut this in half and call this number 0.34. Okay, I'm going to say that delta A is plus or minus 0.34, and usually if I'm claiming that I don't know whether this is a 3, a 3.0, a 3.4, or a 3.5 or a 3.3, then I probably shouldn't be reporting this 4 at all, should I? In fact, that's a rule. You should never have more than one digit uncertainty. In other words, unless this thing is 1.01, then 0.017 might be meaningful because that 7 is such a large fraction of the 1, and you'd call it plus or minus 0.017. But if it's like 0.11 or 0.011, just call it 1. If it's 0.012 or 0.013, just call it 0.01. Otherwise, if you get around the 7, or excuse me, the 1.5, 1.6, 1.7, 1.8, then yeah, go ahead and do that. With all other digits, you should just do 1 sig fig. So I'm going to say we're uncertain about the 10th decimal place by 3 because that's half of this. So what I'm going to do is now report that the actual A value, according to this, my A estimate is supposed to be 57.4 plus or minus 0.3 centimeters squared. So that really should be what we report based on this estimate, but it turns out that estimate's a crappy one. Unless we're absolute goobers, we should never have that bad an error, the biggest minus the smallest. In fact, the way you do it is if you have a given function, I'm going to leave the estimation section and the dimensional analysis section up to you. You can check them out on my YouTube channel if you want. I'm just going to go into deep with this. If you have any function, say of x, so this is y equals f of x, and you have any function x that maybe looks a little bit like this or something, if your x value is here, right, and your sigma x is, say, this quantity from here to here, right, then what you can see is this would be your f of x bar, would be right there, but you'd expect this amount from here to here to be basically equal to df over dx times sigma x. Do you see how that works out? Slope is rise over run. If I multiply the rise over run by the run, I get the rise. Does that make sense? So it turns out sigma sub x is actually just equal to the absolute value of the derivative of a function of x with respect to x times sigma x. That's if there's only one variable. Like, let's say your equation equals y equals mg, where g is a fixed constant. If that's the case, then that would say sigma y should equal just g times sigma m. Okay? But we're actually more likely to deal with functions of many variables, in which case I can generalize this using the Pythagorean theorem and say that the uncertainty in f is in fact the sum of the squares of, now I'm going to do a fancy symbol that if you haven't had Calc 3, or at least the last part of Calc 2, it might look confusing, but trust me, it's really no big deal. It's the derivative of f with respect to x as if x is the only variable. In other words, f has a function of x, y, z, k, w, z, all this stuff. And what we're pretending is all those constants except for x or all those variables except for x are constants. And the x is a variable, and then we just take the derivative. So you treat if f of x is equal to, for instance, 2xy plus z squared, the derivative of f with respect to x, the partial derivative, is just 2y. Because the z is a constant. You're going to ignore that. So that's what I mean by that. So I square that, and then I say times the uncertainty in x squared plus the partial of f with respect to y squared, uncertainty in y squared, plus dot, 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 for however many variables you have. That turns out to be a lot better estimate of it. Okay? So in the case of the area, we had a of x, y is equal to x times y. That means the partial of a with respect to x is just y, and the partial of a with respect to y is just x. So our uncertainty in our area, according to this neat new formula I just gave you, is going to be uncertainty in area is equal to the square root of x squared times sigma x squared plus y squared times sigma y squared. And you can actually do that. It turns out there's a real smart way, though. If I divide sigma a by the actual a, which is x times y, then what happens is I pull in an x squared, y squared in here, and it actually goes under both of them. So this would be x squared, sigma x squared, plus y squared, sigma y squared over x squared, y squared. You see what happens, the x's cancel out in the first term, and the y's cancel out in the second term, and you get, and this is true for all multiplication, you get this sigma x over x squared plus sigma y over y squared. And this number right here is called the fractional uncertainty. That's called the fractional uncertainty, whereas this is just called the uncertainty. And in your statistics speak, that's called the standard error. Not the standard deviation, it's the standard error. Which statistically means you take the standard deviation and you divide it by the square root of the number of trials. So the standard deviation, remember, is your best value, x bar, minus x1. You square that. Then you take x bar minus x2. You square that. You take x bar minus x3 for each of your trials. And then you add all those numbers up and divide by n minus 1, take the square root. That's your standard deviation. The n minus 1 corrects for the data being a little small. If you want the standard error, you then divide that standard deviation by the square root of n, and that gives you the standard error. And that's really what we're supposed to be reporting as the plus or minus on a given measurement. So it turns out whenever you have a product, x times y times z times k times u times w, whatever, you just add these terms over and over, and you will automatically get the fractional uncertainty. So I can say the fractional uncertainty of A is actually equal to, and I refer back to my data that I already had, which is right here. So my fractional uncertainty in my A is actually going to be, using my uncertainty in my x, that'd be 0.02 over my x value, which was 7.44, squared, plus my other one, which was 0.03. Damn it, did I write that again the wrong way? Oh, no, that's cool. That's the other thing. 0.03. Notice they both had units of centimeters, so the fractional uncertainties have no units. And the other number was 7.72. I square that. And what I get is, I'm going to do that in my calculator. I'm going to say 0.02 divided by 7.44. And that's 2.688 times 10 to the negative 3. That's before I square it, by the way, so that's just this part. And then 0.03 divided by 7.72. And that one's 3.89 times 10 to the negative 3. Again, that's just before I square it. So now I'm going to square each of those things and take this, add them, and then take the square root. So using my smart calculator, I'm going to say enter this squared plus enter that number up there squared. And then I'm going to take the square root. And I get 0.00472. 0.00472, actually 473 if I properly round, and that's the uncertainty in the error in the area. Okay, now that's a fractional unit, so if I want sigma A, which is what I have to write as plus or minus, I take sigma A over A and multiply it by A, and whenever you see just an A, that means the average A. So in this case, I'm going to take the average A that I got, which was 57.4362, and I'm going to multiply it by this number, 0.00473 times the average A, which was 57.4368 square centimeters. And when I get that, I'll say times 57.4368. And that gives me 0.2714 square centimeters. Notice I'm back into square centimeters as my unit. So like I told you, this uncertainty of 0.34 was a barbaric estimate. Not that bad though. It's 0.34 instead of 0.27. So I'm going to round this to 0.3. I would have rounded that one to 0.32. So it's not that far off. That's why, you know, depending on how good your measurements are, you don't always have to do this. You can usually solve it with a significant digit issue. So what I'm going to say is A, experimentally, my best possible result, I have to round to 1 decimal place, which we had already decided to do anyways. And that decimal place, we found out, was going to be 57.4 plus or minus 0.2, or excuse me, we should round it to 3, 0.3 centimeters squared. And that is, with our best error propagation formulas that we know of, that is what the actual answer should be reported as. Okay, so remember, when you're taking experiments in principle, and you're hardly ever going to have to do this. In our class, in your lab, your instructor is probably just going to have you use significant digit rules, which says when you multiply 2 numbers, you count the number of sig figs in each of the multiplication numbers, and the one with the least number of sig figs defines the number of sig figs that you get at the end. That's almost always right. If you look on my YouTube channel, you'll see instances where it's not right. And if you're adding or subtracting numbers, you take the number that has the least number of decimal places, i.e. the one with the least precision, and that dictates where you round the answer to. So that is how we actually will be doing it probably in your lab. But if I ran all of my labs, I would be doing this type of error propagation that I just finished showing you. Okay. That being said, I'm not going to introduce it again. I might make a particular homework problem where you can do one just for the heck of having done it. And as an experimentalist, you'll be better for it. But in general, you only need that cool formula that I worked out for any error propagation. Okay, that one right, that one right there. The uncertainty of any function of any number of variables is the square root of the sum of the squares of the derivatives times their uncertainty of that particular variable, right? So this will always work, but it's a lot of work, as you can tell. And the other thing that's important is I want you to remember that the uncertainty is supposed to be the standard error, not the standard deviation. So and most people would calculate the standard deviation first and then divide by the square root of n. But modern calculators have an S and they have a sigma. That notation, to my knowledge, at least within the calculator world, I don't think is standard. So if you ever do it with your calculator, you're probably going to have to do it one time by hand and see which one S is and which one sigma is. The sigma should be really the smaller of the two. So that's one way you can discern it. But other than that, you're probably just going to follow the instructions and use your Sig Figs rules. So remember, when you multiply 2 numbers, the number of sig figs that the least has, that's the number of sig figs your answer will be rounded to. If you're adding or subtracting 2 numbers, the number with the least precision dictates what precision your final answer will have. So if one is only to the nearest tens as opposed to tenths, then you're only going to be able to round it to the tens place. If the number with the least precision is 0.1, then you'll round your adding or subtraction problem to the nearest tenth in a decimal place. And then finally, whenever you put 3 sig figs in a function, you should expect to get out roughly 3 sig figs. So if you take a trig function, 3 sig figs, the answer should be represented as 3 sig figs. And that's even nastier when you actually go to analyze with the error propagation formula. What I do want you guys to do is look over these estimates and ways of estimating. You will find some of those in our practice tests and therefore in our tests. Like one of the questions I gave my students is estimate the thickness of a single piece of paper. And I have like a book like this sitting on my desk. And I tell them that this particular book has 372 pages. That's a very typical estimate problem. All you do is say, oh, I think that's probably 2.2 centimeters tall. Maybe you usually only use one sig fig. So you'd say, I said that's 2 centimeters tall. And then I divide 2 centimeters by 374. And that would give me the thickness of a piece of paper in centimeters. Another estimate problem is estimate the size of the room you're in and tell me how many fruit flies can fit in it. So you're going to estimate the size of a fruit fly. Maybe you treat it as a cube. Maybe you treat it as a sphere. I don't know. But you should be able to get an order of magnitude calculation. That's a really good thing to be able to do. Finally, remember that formulas are about quantities that are measured, and they almost always have units, and therefore they have dimensions. The difference between a unit and a dimension is the difference between a meter and L. So if you're using units, you might have things like length being in feet, inches, miles, light years, or whatever. But if you're using dimensions, they're all a unit, capital L. If you're using mass, they're all a capital M. If you're using time, they're all a capital T. And when you do stuff like that, you can estimate formulas just by dimensional analysis. Like if you know the unit of force is basically a kilogram meter per second squared, then you know it's L m over t squared. And I'd ask you, how does that relate to acceleration and mass? Well, you'd put, let me show you this on a calculation. I know we're a little bit out of time, guys. I'm sorry. I'll just go just a little bit. If I know that force dimensionally, and this is how we write dimensionally, I know it's mass times length over time squared. I know that mass is just dimension m, and I know that acceleration is just is just L over t squared. Then I could say, well, F should equal, I don't know, it should be proportional to mass and proportional to acceleration, meaning the larger the force, the larger the acceleration, the larger the mass, the larger the acceleration. So maybe I raise this one to the x power and I raise this one to the y power to cover all possibilities. And then I put in m L over t squared equals m to the x power times L over t squared to the y power. And I solved that system of equations for x and y. And lo and behold, you will get Newton's second law. That's what dimensional analysis allows you to do. Okay. So I think that's more than enough to get you started. But it's a lot easier working in dimensions than it is in working individual units, because you got to write a little kilogram and all that stuff. But it does get confusing because the M, if you don't use a capital, you're immediately thinking meters, right? So that gets a little confusing. But as long as you remember M, L, and T, that's really all you need. Just about everything should be able to be put into terms of M, L, and T. Before you start your homework, or when you start your homework, if you're having any problems with dimensional analysis, look for similar problems at the end of chapter 1 in the actual textbook, specifically odd ones, and try solving them really quickly. And then check the answer in the back of the book. And once you get the hang of it, you'll be consistently getting the answers right. But you can do cool things like energy, mass, and the speed of light. And lo and behold, you'll get exactly E equals mc squared. And you can do things like distance, acceleration, and time. Distance should be directly related to the acceleration, should be directly related to the time. Put one to the x power, put the other to the t power, or excuse me, to the y power, and solve that. And lo and behold, you'll get a real expression that we're going to use in the next chapter. All right, we're finished with chapter 1, everybody. I recommend for those parts that we didn't go in great detail on that you go to my YouTube channel and look for examples. I'm going to put a list of the relevant examples on Canvas, and I will email you every time I put something new up there. Anybody that doesn't have any questions, you are free to go. I did figure out a way to take roll so you don't have to chat me your first and last name anymore. So by all means, you're free to go. Have a great weekend. Be safe, be healthy. Nobody come home with the Rona. Don't want that. But I'll wait here. The last person that leaves will be me. Everybody else is free to go. Thanks for coming.
Have a good weekend.
Thank you, Professor.
Thank you, Professor. Have a good weekend.
Thanks, Professor.
Have a good one.
Thanks.
Have a good weekend, Professor Younger.
Thank you. You too.
Professor Younger,
Yes, sir.
does your document camera by any chance have like a focus function on it? Just sometimes when you be writing, it just be kind of
It
blurry.
does. What normally happens is sometimes the bandwidth is really the problem. The focus button is this. And you can see it changes. It is actually doing stuff. The good news is I always take a photograph of the pages that I work out and I put that on my Google Docs. So if you run into any problems making out what I wrote, you can always look on the Google Docs to see. Hopefully my handwriting, though it's not great in pens, it's much better with a frictionful surface. Hopefully you'll be able to make that out. So that'll help you. And also, if you ever have that problem during class, just say, Mr. Younger, could you hold that closer to the camera for a second so I can read what you wrote? I don't mind you interrupting me for that. That's certainly worthwhile time to interrupt me. Does that help, Lauren?
Yes.
Excuse me, Professor. Oh, sorry.
Yes.
You can go.
You said, can you hear me?
I can.
Okay, perfect. You said the Google Docs, is that posted on Canvas or is that?
It will be. It's not yet. So it will be, and I will email you when it's there.
Okay, thank you.
No problem. And I always also usually try to do this so people can see my notes afterwards. Hopefully that'll help you guys. Those are good questions. Madison,
I have a
Sean,
question.
anybody
Yeah.
have questions?
I have a question.
Yes.
How do I access the YouTube channel that you have like the lectures posted?
I will have a link to it in our Canvas page, and it'll just say it's under the same link where you'll find the syllabus and the mastering physics and all that good stuff.
Okay, but it just hasn't been posted yet.
Yeah, it just hasn't posted
Okay,
yet.
just making sure. Thank
Actually,
you.
I think it's posted. I just forgot to publish it because I'm a goober.
Okay, thank you. Have a great weekend.
You're welcome. Have a good one, Madison.
Professor.
Yes, looked like Duncan got to me first.
Yeah, I just wanted to say that I emailed you about accessing the Zoom class and I figured it out, so it doesn't really need a response.
Yeah, I saw you came in a little late. Don't worry about what you missed. I'm not counting that against you as far as enrollment or attendance or anything like that. I don't do any attendance grade stuff, but you can catch what you missed on the video once I post it first on Canvas and later on YouTube.
Perfect, thank you. I just wanted to clarify.
No problem. Thank you, bud.
Professor,
Yes.
you mentioned that there is certain material like from Calc 3. Is there anything like, is that going to become a rarity?
Yeah, it's a rarity, but like the partial derivative, I show you a bunch of examples if I really need you to use that very much, and you don't really this semester. In the second semester in 242, you use that stuff a little bit more. But we'll do stuff like line integrals and surface integrals. Those are things that most Calc 3 courses don't cover either. I mean, if you were at MIT or Caltech or Princeton, you might cover it because, you know, everybody's already had 3 semesters of calculus by the time they got there. So they just blow through it and often use like 3 different textbooks. In our class and in physics in general, you find out, and chemistry for that matter, you find out that you learn a lot more math in your physics, chemistry, or engineering classes than you will in your math classes. You're always behind. The math that you need from your math classes is always insufficient to cover the math that you're doing in your science classes. So that is an ongoing thing. The good news is I do a lot of hard work to make sure you guys understand how it's done.
Okay, thank you.
Yeah, and it definitely Calc 3 nor Calc 2 are prerequisites.
Okay.
Okay.
Yeah.
Yeah, Rowan?
Yeah, I actually had 2 questions and 1 generalized statement.
Okay, good for it.
So did you actually get my email about my accommodations form? Because
yes, I did see that.
Okay. Just you hadn't sent me a response.
Yeah, I should have replied to you. I just saw it and put it in my folder so I'd know. All we have to do is when you have a test, you'll keep track of your own time.
Yeah.
and just make sure you don't exceed the time, because I take off huge points for exceeding the time. So like if the test is supposed to be 40 minutes and you, let's say someone has an accommodation of double time, then that person will need to keep track of the 80 minutes.
Yeah. And if I go over the 80, then I'm penalized. Okay.
Exactly. And hardly never does anybody go over. So you'll be fine, bub.
Yeah, usually.
The only bad part about that is if you ever do a testing center test, as opposed to like the Respondus test that I'm requiring,
Yeah.
They have certain rules. Like if you're supposed to be allowed 2 hours for a test, they won't let you start a test any later than 2.5 hours, or maybe even 3 hours before they close. That's the only downside. So just keep an eye on that.
I've had that problem in the old days pre-plague. I had that happen a couple times.
I love it. Pre-plague. Yeah, I agree.
In the olden days.
Back before the Rona.
Yeah. Yeah. As a my generalized statement was my main computer. I'm running this Zoom call on my secondary computer. My main computer, the fan on it just decided to like commit not alive. And so hopefully I'll be able to keep running the Zoom meetings here on my secondary computer, but I'm basically gonna have to swap computers, because that one's fan has just been killing itself for the past
it takes a lot of bandwidth, and it's actually more processor than you imagine working with a Zoom app. I've got some students that are just doing it with their phone. I'm like, oh God, even the biggest of phones, it would suck to try to do this writing or stuff.
Oh yeah. And then my last question was, supposedly I am signed up for a physics lab as being brought by Mr. Ippolito, I believe.
Yes.
But he hasn't loaded basically anything to his Canvas, and I don't know what to do about that.
Yeah, he contacted me earlier. He did not realize he didn't realize he had access to the lab manual electronically. Okay. And it's very normal for our first week or two, the students not have the lab manual. Yeah. And we are allowed under our copyright agreement to, produce a lab or two for a class, even though we've now given our copyright to this publisher. He didn't know he had access. He didn't know he even had the documents. I pointed out to him that he has the documents and showed him where they were. So that should come in. What I do know is his very first lab of this week, he ended up having to cancel because he didn't have that document. That means that lab will be behind by a week. That might have been yours. It might not have been. It doesn't matter. Okay. He might have tried to keep them all the same, in which case he might have canceled lab, but he should have emailed you guys with that.
I haven't gotten any emails from him, and he hasn't even loaded a syllabus or a Zoom
I will speak with him. He's a friend of mine. He's a really nice guy in many ways. I like him and stuff like that. So I'll talk to him and make sure he gets that. I think he's just had some issues with this last. He's having problems with the plague like everybody. Let's put it that way.
Yeah.
I will get him to address that. And you guys should be emailing him at jippolito@tcc.edu. He's been using another email account, and I did ask him to start using that J. Ippolito one.
Mm-hmm. Okay. Just wanted to, since you both work in physics, I would assume you have lots of knowledge about it. So I was just like, may as well ask him during post class.
Yeah, he's a tech nut. He loves musics and videos, that kind of stuff. He really knows electronics in that sense. But he's not very comfortable yet with Canvas and Zoom, so he's still learning his way.
That's fair, especially because.
Lauren, did you say something about Mr. Ippolito?
I had him too, and I basically had the same question as Rowan about the accommodations.
Gotcha. Not a problem.
Have you seen mine?
While they're doing this, the alternatives authors are Serway, Serway, Halliday and Resnick, Halliday. Also Pasachoff, Pasachoff. I think that's Pasachoff and Wolfson, and it's also Halliday, Resnick, and Walker. Another one is Fishbane, Gasorowitz, and I can't remember the last name of the last person in it. Those are all excellent textbooks. They work really well. There was another one, I can't remember for the life of me, that was really well written, and it was meant to be taken while you're taking your calculus class. I want to say it was like Tipler or Behe or something like that. I can't remember which author it was, but that's a good one as well. So if you find anyone that's called University Physics or Physics for Scientists and Engineers, it's probably going to be pretty good. If it's in its first edition, it may be wonderful, but there's a chance it's going to be crap. It takes a long time to get to a second and third edition where things are starting to level out and not have a lot of errors in them. I know that's more than you asked, but I just thought I'd put it on the video.
Okay, I appreciate it.
No
And
problem.
and my second question is the homework assignment in Canvas or is it in my lab?
It is, you go through Canvas to get to it in my lab. If you go
Okay.
the other way, it'll mess things up. So make sure you go to Canvas and then click on My Lab and Mastering, and then you'll find the homework in there.
Okay, I gotta set up my account for my lab. I have yet to do that. I'm gonna do it this weekend.
No problem. If you have problems with it, let me know. And well, first you need to call the publisher themselves with either email or contact them via phone or have them call you. If you still have problems, then email me and I'll try to set up a Zoom meeting and help you with it.
Okay, thank you.
No problem.
Have a nice
Anybody
weekend.
else?
Have a nice weekend.
You too. Thanks, Deshaun. Lauren, Rowan,
I think my last
Andy?
Sticking
my last
around.
question was just going to be, do we actually need do we need to like buy a passcode to access the homework, or do we just have to go?
If
Here's the
you go
website.
to the student store or student store in Virginia Beach and buy either a binder ready or a hardbound book or whatever, it will automatically come with the password, the passcode.
So, but we
But-
do need one to access the homework.
Yes, yeah, that's the only way you can access the homework. They
Okay.
give you like a 2-week grace period, just because they know sometimes things will be back ordered.
Yeah.
And some of the book publishers, like textbook brokers, some of them will take an old book or a used book and shrink wrap it with an actual access code, and that's a little cheaper than sometimes what you get. So if you want to try that, you can do that as well. Amazon might have it. The ISBN will be on my syllabus, so you can just check that out, and
Okay.
that'll tell them that you need the book and the access code.
Yeah. Okay.
Okay.
That's it then for me.
All right. Have a good one.
See ya.
Yeah.
Take care. All right. I'm going to go ahead and sign out. Looks like everybody got their questions answered. Andy never asked anything. Are you still there?
Yes, sir. I'm good.
Okay. Have a good one. Bye-bye.